About hardware hacking. Welcome, Craig.
Right on. All right.
Speak loud into the microphone. Everybody else, quiet down.
Hello. There we go. Everybody hear me all right? I have a tendency to move around, so I'll try and stay right here. So yeah, actually, I was supposed to talk here in like an hour from now, but it turns out that guy's trying to fix his flat network after seeing Jason's talk. So I'll go ahead and step up here. So the purpose of this talk, Hack Mode Enabled, I was trying to give a talk that both trained and kind of enlightened some people, because if you talk to most people that aren't in our industry, they have no idea how bad hardware security actually is. And Hack Mode Enabled, actually, the name of that came from a product I was testing where literally in the bio screen it said, would you like to enable Hack Mode? Press 1 for yes. When you pressed 1, it dropped you into a root prompt. So a little bit about me. I work for Coalfire. Before that, I spent 12 or 13 years building the majority of the wireline and some of the wireless infrastructure for 911 in the country. And then some random certifications that mean I may or may not know what I'm talking about. So this is the screenshot that I was referring to. It's interesting. Most people, like I said, don't have any idea what hardware security is or how bad it is. Funny story, last night we were at one of the hotel bars around here, and we were talking to this husband and wife couple that just happened to be the poor schmucks that were sitting next to us. And she's like, oh, what are you guys doing? I was like, oh, I'm giving a talk on hardware security. She's like, oh yeah, I saw that thing about the listening on the TVs and stuff, but that's not real. No, it is. It's definitely real. And she's like, well, how bad could it be? I said, I don't know. Where's your TV? My bedroom. Oh, but it's not a smart TV, right? I mean, for the record, buying non-smart HD TVs right now is actually pretty expensive. She's like, oh, well, it's got a camera. And I was like, oh, I'd move it. But yeah, they just don't understand. And with the Mirai botnets and a lot of that stuff coming up, more attention's being paid to it. I know the FCC and some of those guys are talking about putting some more regulations upon security and stuff like that on these embedded device vendors, because in reality, it costs you $30, it's costing them $15 to mass produce, and it doesn't really matter to them. We need to make it matter to them. The hardware, though, is just a means to an end. Like they've proven lately with the botnets, and as we saw from the CIA dump and all the video recording and audio recording on your guys' TVs, it's really more about the software that's running on these devices and what that can enable. Fun experiment. Go buy some used routers off of eBay, sometimes Amazon too, and take a look at the code that comes on them. Usually if you're buying them used, it comes with stuff not necessarily intended from the factory. And it takes all of 5 minutes to backdoor a router and throw it back out on eBay for $10 less than everybody else, and it'll sell right away. So one thing that kind of gets me, and the reason I do a lot of these talks and try to teach people, is they think that once you have root access on a device, like if you go over to the IoT village that Chris Robertson and those guys are doing, it's not about getting root on the device. It's the software that lies behind that, and a lot of people equate that to hacking in the 90s, which is actually true. It really is that bad. I was working on a device earlier this year. Once you got connected to the device, you could see that there was a wireless access point that was filtering on a Mac. The OUI was the device of that company, and anybody with that OUI can then connect to that access point, where they then transferred clear text credit cards over the Wi-Fi back to their processing station. And if you just got root on that device, you totally would have missed that. So this is kind of the methodology that I have put together, that I kind of run my personal and business kind of stuff through. So disassembly, taking it apart, component identification, figuring out what's on it, because if you don't know what's on it, it's really hard to interact with it. Pin-out reversing, which can be difficult, most times not. And then you connect to the interfaces on the device. And then what you realize is you connect to the interfaces and you download the code, you realize there are actually more interfaces that you can then connect to. So that's why it's kind of an iterative cycle. So where do you get the things? Buying the new smart things can be really expensive, especially if you want to go buy a Nest thermostat for $250 and then you brick 4 of them trying to figure out what you're doing. Luckily, there are beta programs out there that you need to watch the T's and C's on, but for the most part, after your beta cycle is done with them, the hardware is yours to do with what you please. And here's a couple of them. TP-Link, Linksys, and Netgear all have beta programs, and they're designed for you to test their hardware. But in reality, after the hardware period's done, you break out the soldering iron and the screwdrivers, and you avoid the warranty. Flea market's another good place. I'm actually from Denver, and we have this ginormous flea market. It's like a 2 square mile garage sale. It's pretty odd, actually. eBay and Craigslist, like I said, and even garage sales. People sell their old cable modems that they have no use for nothing at garage sales. Another great place to pick those up. So avoiding the warranty. That's the funnest part. I include this slide in here because this is what I use for reference. They all try and be like creative and have some cool way of keeping you out because you don't have a screwdriver kit. These are the common screwdriver bits that you will see on the bottom of cases. And it's also worth noting that if you don't have one of these, that if you, I was in a class one time, I think by Joe Grand. He was like, yeah, if you don't have one of these bits or they have one different than that, just melt a Bic pen to the end of it and stick it on there. It actually works. A simple X-Acto knife set like that, I think I paid, I don't know, $3, $4 for that on Amazon. And then a heat gun, because a lot of the plastic parts sometimes are melted together. So a little bit of heat take those apart. So, tamper resistance. This is actually on a device I was working on late last year. And they're like, oh, but you can't get in. And if you do get in, we'll know because there's tamper sensors on there. Okay. Does it look like anything is pressing? Oop, there we go. Nothing actually pushing the tamper sensor in. So you take it off, and I was curious to see if they would call me, haha, we caught you. So I sat there and pushed the button repeatedly for 5 or 6 minutes. Eventually they called like, see, I told you, when you open that thing up, we'll know. I was like, actually, I've been sitting here drinking my morning coffee, pressing the button to see if you would respond. Another thing that software and hardware companies like to do is put epoxy on there, right? So if we cover it in this black epoxy, you won't be able to read it. It's great. So that heat gun will also take off some of that epoxy. And this right here is just a fail. So this piece of hardware was designed to be used in a marine environment. So they were worried about corrosion and things like that. So they actually covered the entire thing in silicone and then put the epoxy over the top of it. I actually took that off with my fingernail. Like, oh, how'd you get that off? No. Literally, all it took was a fingernail because they put all of the epoxy on top of silicone. So, component identification. What do you guys see? This is really where you guys are supposed to answer. Anybody?
CPU, flash, SRAM.
Yep, right on. So it is a wireless access point. We do have a CPU right here, some through-hole pinouts right here, some RAM over here. These little chips, kind of an important note, especially for those just getting into this. These little 8-pin packages over here look like little flash chips, but in reality, they're not. They are power converters. They work with a power system. So if you plug some of your tools into them, they will not function after you do that. So, always have spares and check first. But yes, correct. So, we have a Broadcom package. It is a MIPS core. We have a serial flash chip, and then some memory, which really doesn't matter in this case. Also worth noting, this was end of life. This was a fairly new device I bought. And this was an end-of-life chip on it. So they really do just farm this stuff out to the lowest bidder. In this case, brand new hardware, and they were putting end-of-life, unsupported cores in it. So some tips and tricks for kind of identifying components. It is often very difficult to read them. So you have these helping hands here. I don't know that they're much help, actually. I've bought 3 or 4 of these, and I've never really found one that worked, other than having the magnification is helpful. The soldering iron here, don't use your $150 or $200 whatever soldering iron for removing epoxy and things like that off of the board. You'll ruin it, or at least make it not function as well for its actual intended purpose of soldering. And you can just buy a $7 or $8 cheapo soldering iron and use for that purposes. This random dude with a camera here, I have no idea who that is. But a camera is very helpful, especially like the new iPhones, where they have the actual optical zoom in them. Very helpful for identifying components. Down here on the bottom, this little white thing right here, I don't know, how many of you guys have actually done hardware work before? They said a lot of students were coming here, so I wasn't sure. So we got a few guys. So that is a flux pen. Normally you would use it for soldering and different things like that, but it's great for, I don't know what the term would be, but the etch chips where they have the component information etched in there, but not backfilled with some kind of white so you can actually read it. I find that covering it with a flex pen, which is clear, and then letting it dry makes it a lot easier to read what is actually on the chips. And then just a brush and your standard X-Acto kit. So, arts and crafts time. I love this picture. It offends some people because she happens to be a female, but if there was a dude on here, I would do the exact same thing. But so some of the kind of stuff that you need, the headers, the soldering iron, I definitely recommend something that you can control the temperature on for solder. And I've actually got a picture here later in the deck that shows you kind of why you want to do that. Soldering wires. The headers, most times, the single or double row headers will work just fine for the majority of what you need. You can go to different places online and get some of the more fine pitch stuff, but it's really not needed most of the time. So the first thing you want to do is find the ground. If you don't do this, you will end up ruining tools. The ground, usually the best place to find it initially, sorry, it's kind of weird setup. The best place to find it initially is right next to the power plug. It's a through-hole connector through the board. Just use your multimeter. Anything will work. I mean, you can get these things for $5 or $10. This is a Fluke 117, I think, which is what I use. It just seems to work better. And then right here, just take a picture and work out what pins are what, so you know where your ground is and where your voltage is. Most of the stuff that you'll be working on for the small IoT stuff or the stuff in the IoT village over there is 3.3 volts. So physical countermeasures are kind of a thing. On higher end devices, you'll see them more often. This is on a SMB type firewall. I forget what vendor it was. Anyway, you'll see here, it's got a row of headers on top and a row of headers on the bottom, connected by through-hole ports. And then in between, there's resistors. There is unsoldered connections over here. There's a gap in the traces. And it turns out on this one, you had to connect these holes just right so the resistors were in the right order for the headers to actually be able to get the JTAG connection. In this case, it was JTAG they were trying to hide from the typical end user. So some of the more common interface types that you'll see, UART is the 3-pin serial that you'll see on most of these devices. The vendors generally don't even try and hide this, although on some of the versions of the TP-Link routers, they do actually have solder gaps, trace gaps, and things like that to try and stop you. SPI, or serial peripheral interface, is another common one. I2C, how chips talk to each other. JTAG, which is probably the most misunderstood or misused term in connection. And we'll talk a little bit about that later. CAN, something you'll see in cars, seen in ATMs and other things like that. And then RS-232 serial. So any of you old telecom guys out there, Cisco guys, that little DB9, that's actually running RS-232. If you connect a UART serial adapter up to that, I've actually done this on, we'll call it on purpose, but it was on accident. If you hook your connector up to that, it actually is 3 times the power, and given enough time, it will actually melt the serial chip off of your adapter. That was expensive. So pinout reversing. For this, I use the Soleil Logic Analyzer. It's just about the best way to go, at least on I'll just say our budget level. $100 on the low end, and depending on the model, they actually have an educational discount for you students out there at 50% off. So you can get these for $50, $60 shipped. It's a great deal. It's not perfect, right? So it is a logic analyzer running on the CPU of your machine, and it does employ sampling. So the output that you'll see from the Soleil is slightly different than you'll see on something like an oscilloscope, but it works just fine for our purposes. So here, this is actually the device here is plugged in, and this is the output when it's booting. And I lost my header off the bottom of the screen. Anybody know what that is, or what does that look like? What's that make you think of? Anybody?
Probably like a boot console or serial output.
Yep, very good. That is the boot log of that device. Fortunately, the Soleil will decode async serial, no problem. You just have to set the configuration in here, and then voila, you have characters from the little up and down marks showing you the boot log. And it is the Broadcom ARM core that's on there. So, another way of doing this, although I don't use this as often for this purpose, but the JTagulator created by Joe Grand, which is also a very helpful tool, roughly $180 to $200, so a little higher end on the I do this at home budget. But it will go through and iterate through the different baud rates for that async serial connection and give you an idea of what it is going to connect at. As you can see, it still takes some manual reviewing, but it's very helpful. So after we've identified this interface and we know, hey, this is a UART serial interface, how do we connect to it? So there are a few options for that. The most common that I hear of in talking to different people is the Bus Pirate. It's also, I believe, the cheapest. I think they're like 15 or something like that, odd dollars. The Shikra, which is my favorite, made, I don't know if it's made or just sold by Exhibitor, but you can see that on their website. I think it's like $40. And then on the bottom right is this TIAO multi-protocol adapter. The nice thing about this is you can do 2 interfaces at once. So if you're using JTAG and serial, you can use one device to connect to both, which is pretty helpful. So using the Shikra, there's the pinout, and it oftentimes is very helpful to have multiple of them. In this case, I was connecting to the JTAG and the serial interface on this board. And the pinouts are here on the right. Literally, all you have to do is plug it in, match the picture, and you're off and running. The link to that picture also is in the bottom right-hand side of the screen. So connecting to UART. It's just a serial device on your machine. So depending on the flavor of OS, it looks a little bit different. On Mac and Linux, it's going to be in the /dev folder. In Linux, it'll be TTY USB 0. On a Mac, it'll be cu.usb serial or something like that. And then on Windows, it's going to be a COM port, which is a little harder to figure out, but through guessing, you'll figure it out. And then all you have to do is supply the baud rate, and look, after we connect, we have a root prompt on that device. In this case, it's a BusyBox shell. But now what? Insert cool GIF here. So this gets into a little bit of the hacking in the 90s mentality. So if you take a look at this device, it's running a web server on port 55,555. And then it's got some S-tunnel connections back in that at the time we didn't know what they were, but in reality it's an encrypted channel that they were using to send card and payment information back to their home office. And then it's also got Telnet open, because everybody needs Telnet. Especially, it's just one thing I don't understand. Put a little bit of effort in. You're already doing SSL encryption outbound for your payment method. Why not use SSH for management and connections? But it gets better. So their web server, THTPD, was unconfigured by default. So they left it just stock flavor the way it was from the manufacturer. Those of you that have ever messed with this before know it runs by default as root. And unless you specify a directory for it to run in, it assumes it has access to the entire file system, as you see right there. So through this device, you can read the shadow file or do anything you want through this web server as far as accessing it and downloading code. Another one is wireless. So that Linksys WRT54GL that I had showed in the picture, the top left screenshot is actually what happens when you press the little status button on the front of the device. This all dumps out to serial, including the clear text copy of your key. So that does require physical access, right? But if that button is pulling the clear text copy of your wireless key out of there, it's sitting somewhere in clear text in the software, which is not good. The bottom right-hand side, this was on a device used to charge very expensive cars. We'll go with that. And it had a wireless connection. It had an AP passphrase and all this kind of stuff, but we were able to read the configuration, which means we know what the client passphrase was because they left their web server completely unconfigured. We had full access to their device. So the file systems. It's a little bit different. So if you haven't messed with this stuff before, the serial flash gets imported into the system and then mounted. So that is why you'll see the root file system right here is actually something called an MTD block, or a memory technology device block. That is how these systems load up in what is in flash. So oftentimes they leave out the good stuff, right? So if they've got a partition flash that they use for upgrades and they only want that mounted when it's going to run an upgrade, or they only use it for building, they will leave it unmounted. And these are some of the commands that I've used over and over again. It's in my little cheat sheet text document for how to mount these devices. Because oftentimes that's where they leave the good stuff. And there's the link here at the bottom right. It's got an entire sort of presentation, if you will, on how all of the MTD blocks and MTD devices work, for your reference later. One difficult, or can be difficult, part of this is how do you get the interesting stuff off to the file system? So in this case, there was no telnet, there was no SSH. Some of these systems actually, believe it or not, come shipped with the netcat/e option, so you can shovel a remote shell. Like, they don't even try. In this case, though, I had no other way other than my screen to get data off of this system. So you use OpenSSL, which was preloaded on there, and then just base64 encode the entire serial flash off to your screen. It took about 45 minutes over lunch. Went and grabbed coffee, came back, and I had it downloaded, base64 decode it, and you have the entire flash device on your remote machine. And it looks cool when your boss comes up. And he's like, "Oh, what are you doing?" I was like, "I'm just downloading the binaries off of this machine." "What's that scrolling on your screen?" "It's the binaries." It's hacking. It looks cool. So this is on another device that I was testing late last year, which was awesome. So this was for an engagement at work. So I had access to test the entire back-end infrastructure. In the spirit of Jason's "you can't sue me" thing, don't test the back-end infrastructure of a device that you haven't been contracted for. So just because you can get access to one of these things and, say, connect back to their cloud because they use the same SSH key everywhere, don't do it unless you actually have permission. In this case, they happened to leave their build script on a different partition in Flash, and when mounted up, they left their SSH public key and private key without a password in that device. Not only that, they had the history file of what IP address they connected to, which you'll see down there on the bottom. So now we have their SSH public and private key and where they're connecting to on their build server over SSH. Think that might be a problem? They did, because I connected in, left them a nice little ASCII art banner on their login screen. So JTAG, like I said, JTAG is something that is very misunderstood. I love talking about this stuff. So you get to talk in, and the guy's like, "Oh yeah, this device had JTAG. That's like InstaRoot." No, not at all, actually. It is rather complicated, but to boil it all down to what a beginner to advanced kind of person, intermediate kind of person is going to need to know, there's 4 pins that matter: the TDI, TDO, TCK, and TMS. The reasons why I say they matter is that's what you have to have. It's the minimum implementation for JTAG, and it's also what you're going to need to set on the Soleil logic analyzer to properly decode that data. So some of the options here for connecting to JTAG, once again, you have the Soleil logic, or the Shikra over there on the left for about $45. I think they're actually in stock right now on the exhibitor's website, and they go in and out of stock frequently, so I always buy a couple because you end up breaking them. The Seger J-Link is a good device, and that's the one in the center. They do also have an educational version which brings the price down. You just basically drop a 0 off the end. And you can buy the $600 device for $60 if you're using it for educational purposes and not commercial. The one on the right, the Lauterbach, the only reason I put that in there is because some hardware manufacturers limit how you can connect to them, and OpenOCD, which I'll talk about, doesn't support all of the chips. This Lauterbach does, and some of the certain Marvel cores and things like that, you need that higher end device to connect to it, which is kind of unfortunate, but the support for OpenOCD is really good. So this is where the JTagulator really shines, and really what this device does is enumerate through all of the possible pinouts for UART or JTAG, and it does it fairly quickly. You'll see the options here on the left. There's the ID code scan and the bypass scan. So they take anywhere from, 5 or 6 minutes to 20 minutes, depending on the scan and the number of devices in the chain. But the output you'll see over here on the right, it identified the TDI, TDO, TCK, and TMS, so now we can go ahead and connect to that. One thing you will need, though, is the device ID, which is down there in the bottom right-hand side, that 0x05352117F. That is the device ID that you will need to have so you can find the appropriate OpenOCD configuration. So how do you connect to OpenOCD? You have to supply it 2 different parameters, both the configuration file for the device you're connecting with and your target. So in this case, we're using the Shikra config, which you can get, I believe, off the exhibitor website. It doesn't ship by default last time I checked. And our target board is that ARM core right there. So, all right, now you hit enter, and you're like, wow, it errored out. That's not cool. Now what? Another great resource, the OpenOCD on Freenode, full of awesome people that love OpenOCD. A great resource. You drop in like, hey, I'm trying to connect to this device and I can't figure out how to do it. There is 100 people in there willing and ready to answer your question, most times with minimal heckling for IRC terms anyway. But after all of that splur out of error messages, you'll have 3 open listeners on your machine. Port 4444, 3333, and the dreaded all 6s. I don't know why they picked that one. At any rate, all 4s is a telnet listener where you can connect in and then actually get the output from your JTAG OpenOCD session. So if you tell that into that, you'll see what we have here below. It'll give you the target name, the architecture type, its endianness, and then what the state of the machine is. In this particular case, it started up halted. So I don't know how many people are doing the CTF in here, but there's some reverse engineering challenges in there, some of which GDB could be helpful for. GDB also can be used on more than one platform through the multi-arch binary. So you can load up MIPS, ARM, x86, x86, 64, whatever you want to do there. You can toggle that on, and as you can see here, through that telnet session, we have access to all of the memory and the registers. So kind of my pet project, I don't like all the minutia. I want to get in and do the sort of fun stuff, which is why I started creating this tool called Serial. My daughter actually named that. I was sitting there working on it, and she was trying to get me to do something else. She's like, "Oh, what are you working on?" I was like, "Oh, this Serial program." She's like, "I like cereal. Can I have a bowl?" All right, fair enough. We'll call it Serial. But at any rate, should be releasing this here on my GitHub within the next week or so. But the whole purpose here is just kind of automate some of the minutia. It will. One thing that is very helpful in hardware hacking is getting that boot log so you can see what the different boot up processes is, so you don't miss the fact that hack mode is actually an option in hardware these days. So it'll go in, it'll tell or connect through your serial device, and then simultaneously connect in via JTAG, restart the device, capture the boot log, and save it off to a file. Another tool, a lot of vendors like to have unique passwords per device, which is a great practice, just like we've been preaching in the Windows domain forever. But another good thing to do is parse the boot log for said password. I believe there was 2 or 3 devices recently where this actually had happened. They had embedded the password in the boot log. And what the password guessing module will do is download the boot log along with a couple of different word lists and just spew them out over serial. It takes a little while to run because it is a slower protocol, but I have found that to be very successful. And it'll do other things like guess your baud rate and stuff like that to iterate through, sort of like the JTagulator would. But it's just another option in there. It'll also display what serial ports you have in there, what your OS is, because it uses the OS value to determine how to connect to the serial device. So after you've connected to this device and you've enumerated all the interfaces that you can find, and now you're working on reverse engineering, now what? So there are a few options for this, ranging from free to pretty darn expensive. I typically will use IDA Pro for reverse engineering a lot of this stuff just because I have a license. Radare 2 is also a great platform. It doesn't have any decompiler support, but it will help you get there. Binary Ninja is kind of a newer player to the game. For those of you that can't afford or don't like IDA Pro past the free version, Binary Ninja's got a kind of different way they're doing things. So they're developing this intermediary language. So the thought is this one intermediary language rules them all. It doesn't matter if you're interacting with a MIPS core or an ARM core or whatever you're doing, whatever code base you're working with, this one intermediary language that can be scripted and coded against will do it all. So you don't have to learn how to do each one individually, and you can actually automate a lot of these boring tasks, which is really nice. IDA Pro, like I said, the free version is awesome if you're just doing it for a small purpose. One sort of tail there. So IDA Pro also has a really good debugger built in that is great unless you actually need to step through like a large program. IDA Pro, the free version of the debugger, limits the amount of steps or continues that you can use. So we were working on an ATM project a couple of years ago, stepping through some of the code for how they encrypt USB devices on their system. And we were just about to where they copy the keys into memory, and we hit the maximum amount of continues. That was weird. The voices from above. We hit the maximum amounts of continues that you can use. And of course, it had a watchguard running, so when the debugger stopped, the machine restarted, and we lost all of that work. So just a word of the wise, if you're actually working on something like that, it's going to take a while, don't use the free version of the IDA debugger. There are plenty other options out there. Here is some sample output of Radare 2. It'll do code blocks similar to the way IDA does, and the hex dump as well. This is an output from IDA Pro. The screenshot on the left is the normal output, and then the bottom right is the decompiler output. Like I said, the decompiler is a little more expensive, though. It is, I think, $2,000 in architecture, something along those lines. So other nice to haves as you're doing this, a desktop power supply. just because it makes things like glitching and stuff like that easier. I have the USRP in there because that's what I have, but there are other options. It's basically an SDR. So it is amazing what gets broadcast out over the wire. If you've never looked at, say, 929 megahertz, like roughly in that range, if you've never looked at that over wireless, it's really entertaining, and the amount of data leakage that is out there from some institutions is amazing. They're like $50 for a cheap one. Highly recommend you have it in your kit for normal stuff, as well as hardware hacking as well, because a lot of this stuff has RF components too, like the security alarms and door alarms that you'll see over there in the IoT hacking village. Hot air rework station up there on the top right. So that's for taking certain chips and stuff like that off. The bottom left is it's a Zeltec, I think 610P or something like that. But it is a chip read writer. So you can pull code straight off the chips if you don't have access to any kind of interface on there. And you can get them specific for a specific package and make of chip, or you can buy a universal one like this. The bottom in the center is a RFID reader writer, the Proxmark 3. Also an awesome tool to have in your bag and can make for nice office pranks. Reflow oven, or the cheap man's version of it, a toaster oven in the bottom right-hand side. First of all, don't eat anything cooked in that after you use that to reflow a device. And second of all, look at the type of plastic is on there, because some of the plastic will melt. Also, if you have plastic capacitors on the board you're trying to reflow, don't stick it in the oven. They just go poof and emit a really foul smell and some smoke. All right, so what's next? There are several resources up here for training. Both Joe Grand's training that he does at Black Hat and DerbyCon, and the exhibitor training that they do all over the place now. And then the EEV blog. So I'm not an electrical engineer. Never had, never could. Probably not smart enough to be. But there's this guy that in Australia that runs the EEV blog, and he just nerds out over this stuff for like 2 hours a week that he dumps out onto a webcast. And he is absolutely fantastic. Vendors will send him hardware to have him tear it apart and review it over the internet. I highly recommend, if you have a few hours, go browse around there. You'll learn something for sure. Embedded.com has a ton of resources for doing this kind of stuff. And their beginner's corner actually pulled some of the JTAG and information and UART information off of there. So I would definitely go check out that. So I know I went through there kind of quickly, but I was trying to make up a little bit of time. Do you guys have any questions for me? Bueller? All right.
This guy's out. We're gonna throw him out right now, Chris. I'm sorry.
Oh, I thought somebody was calling in for a question because it's being live streamed and stuff. No? Oh. We could have, it would have helped my ego a little bit if somebody was calling in for a question. But, all right, so I'll be hanging around out here today. If you guys have any questions, let me know. Love this stuff. More than happy to talk. So, and thanks for coming. And thanks for everybody that puts on the conference and in the venue here. Without people like that, this stuff wouldn't happen. And it is a ton of work. So, thank you.